Hello, this is Alan Folmsby, and thank you for joining me today on the live broadcast on YouTube. Today I'll be talking about the wavefunction velocity, and this will be brought to you from New Britain, Connecticut, and it's kind of snowy out today, and so I have some pretty cool things to tell you about concerning temperature and the wave function velocity. The atomic wave function dimensional velocity is described including replenishment of the wave function when photons are emitted or absorbed. As an overview, let me just point out right away that the velocity of the wave function is 0.2 meters per second. That's about 8 inches per second at 1 degree Kelvin. This is part of the grand unified theory called the theory of enough. For all practical purposes, this theory provides enough science, and it fills the gaps in physics that occur in the standard model. I'll be talking about the frequency of the wave function and how that can be related to the photon frequency. At 1 degree Kelvin, it's 132 megahertz, but at higher temperatures, it can be faster. And the wave function is also called the magnetic line of flux. Now, flux is defined like the ampere or the Weber to be length times velocity, 3 dimensions, 2 space dimensions, and 1 time dimension. So here's an overview of what I'll be talking about. S is the characteristic speed of the atomic wave function at the, it's a flat membrane. And S is equal to a speed, which is momentum divided by area, 0.2 meters per second. The momentum is taken from Planck's constant, divided by the atomic scale length of 2.41 angstroms. Now the area of that calculation is Boltzmann's constant, and X-rays can be emitted at a low temperature plasma. And these are the things I'll talk about. Now the replenishment theory unifies gravitational and atomic continuum fluids. There's an 8-dimensional mirror in each proton. There's 4 gravitational dimensions and plus 4 wave function dimensions. Gravitating matter is just neutrons and protons. So the 8-dimensional mirror is shown in this sketch here. And the black is just outer space. The blue in the center is a proton. And then on the right, you can see 3 space dimensions going into the proton, like little tornadoes. And the white is the time is coming out of the proton. And this balances the space-time continuum for the conservation of continuum. Now there's 4 more dimensions in red and white here, where the electron is black on the left, and there's 2 red space dimensions going in, and 1 time-like dimension in white coming out. So this can be seen in closer pictures in my book, The Charge Distributions on the Nuclei. My new book has just been published recently. There it is, pretty heavy, 8.5 by 11 size, huge, and it's 535 pages. And this picture, I'll show you right here. Here's my book, and the picture you were looking at there of the wave function, it's in this book, and you can buy this on Amazon.com for about $101. It's heavy, 4-pound book. Now the 8 dimensions are listed here. X, Y, Z, and T are like liquid space going into the proton, and time is coming out of the proton. And then the 4 more dimensions, H, X, H, Y, and H, Z, are coming out of the proton, and the TH is going into the proton. So that's really the opposite of the gravitational dimensions. It's a mirror image. So now this mirror in the proton, it's a mechanistic theory replacing the quantum chromodynamics, the quark theory. The deterministic wave function is not a probability cloud. It's something with exact definitions. And it's not really about where the electron is, as that could be even a free electron far away that is also paired with a proton. Now, electrospace and magnetime are nicknames for the dimensions. And instead of meters and seconds, you can use eters and ekins for the atomic wave function during acceleration. And the atomic wave function has a curved coordinate system for the ionic situation, or atoms. Expansion of the wave function subuniverse is analogy for our universe, which is expanding also. Electrons do not cause gravity. Protons and neutrons do. Energy does not cause gravity. Energy is about matter and their wave functions. So here I have a picture of photons, and on the right we see the picture of photon emission. So we see on the right there's an electron, on the left a proton. And the 8 dimensions of the proton are in this sketch. And now in the middle picture, you see a red photon is coming out from the wave function, leaving gaps in the black and white lines. And now that causes an imbalance in the bottom picture. After the photons moved away from the ion, there's an imbalance. So you see different sizes than it started with. And that'll cause a replenishment to occur where the energy change in the atom is due to the proton replenishing the wave function with a momentum. And the photon doesn't contain the energy itself. It has 2 dimensions, like a space-like and time-like, and that gives the property of a velocity-like property for the photon. It's not energy the photon's carrying. It carries something like velocity. And when that hits another atom, then that will be combined with momentum to give an energy change. So electrons are discussed in this one here. They don't cause gravity, but their mass is affected by it. Mass is an area of the space-time continuum. And gravity is a volume effect, not an area effect. And pairing always occurs between every electron and one proton. Even a free electron is paired with a proton. And outside of that pair, induction pushes other pairs around. So there's the carbon atom, and it could be ionized, and it could give off, this is the nucleus, and it can give off a photon, and these protons, the white protons, will then replenish the atom. So there's 2 views of matter I like to use, the pair view and the universal view. The pair view is a simple flat image, and atoms have several electron-proton pairs. The universal view of molecules would show a more complicated picture of the same thing with a twisted coordinate system. Chemical bonding is the wrapping of wave functions around each other. Electrons orbit by wrapping flat lines of flux. Electron orbitals and just how they orbit each other. The electrons don't orbit the nucleus like a planet around the sun. Electrons orbit by wrapping flat lines of flux around each other. These are wave functions. And there's abstract units of measure. At the top we see three types of area: mass, charge, and Boltzmann's constant. Temperature is a potential, which is velocity squared. Generally, it's the velocity of electrons and the velocities of ions. And so these velocities are not the same as the wave function velocity, though. So there's two types of velocity I'll be discussing here in the next 10 minutes. Now, there's two kinds of acceleration, Newton's constant g and Coulomb's constant k. So the ratio of those two things can be dimensionless. So I'll just get a drink here briefly. All right, now Planck's constant is about angular momentum. That's like a wheel on an axis spinning around, and the radius of the wheel is called the arm sometimes. And that's angular momentum, but there's also a linear momentum, and in gravity, that is the proton volume divided by 5 nanoseconds. And these typical radius values is the proton radius, the Bohr radius, and the Folmsby radius, 2.4 angstroms. Now, the momentum in a wave function is important, as I was saying, that energy levels in atoms change by multiplying the momentum times the velocity property of a photon. And the atomic wave function uses Planck's constant. It's a linear momentum multiplied by the length of an arm. Now, the length is called the atomic scale, 241 picometers. And the linear momentum is calculated by Planck's constant divided by that 2.4 angstroms. And the result is this value, 2.75 times 10 to the minus 24th cubic meters per second. Momentum is equal to area times velocity. This is how I'm getting the velocity of the wave function. And comparing gravity versus the wave function, at 1 degree Kelvin, the wave function momentum is 2.75 times 10 to the minus 24th cubic meters per second, but the gravitational momentum of free space is much smaller, 7 times 10 to the minus 37th. Now, the ratio of those two momentums shows the strength of the atom versus the weakness of the proton gravity. And the ratio is 3.9 trillion. Now, we can calculate the velocity from momentum by the momentum being equal to area times velocity. And area is Boltzmann's constant, k. And the velocity we'll be calculating. And normally momentum is mass times velocity, but mass is a different type of area, but it's similar to Boltzmann's constant k. The velocity of the wave function then is 0.1993 meters per second at 1 degree Kelvin. That's just by making that calculation there of the equation. It can be velocity per degree Kelvin, and s, the small s, is the speed of subspace. That's the wave function velocity. Big S is for gravity. It's the speed of space for the momentum divided by area for gravity. So space is sinking into the Earth at 4.9 meters per second. And for a nova star, the speed of space can be calculated from this formula r rho v over 3mr, where r is the radius of the star, rho is the mass density, v is the proton volume, O and m is the proton mass, and r proton radius. And from that you can solve for the point at which a star will go nova. Now what I'm going to do is use all this speed of subspace, small s, to solve for photon frequency. And here's where the calculation is. It's quite simple. It's s equals momentum divided by area, p over k, where k is Boltzmann's constant. And the momentum, p, is Planck's constant divided by AF, h over 241 picometers. And the result is the momentum of the atom, 2.75 times 10 to the minus 24th cubic meters per second. And the radius being used here, AF, is from the atomic scale formula from last week video, and that's 241 picometers. So doing that calculation then, S equals P over K is about 2 meters per second, 0.2 meters per second. It's the velocity inside an atom's curved coordinate system. And people are interested in the solar corona, and you get different things in space, outer space, and the wavelengths of ultraviolet, X-ray, and gamma rays are as follows. 19 million femtometers for UV, 11 million femtometers for X-rays, and gamma rays are a fraction of a femtometer, 2 millionths of a femtometer. So each photon has 10 to the minus 5th joules. And gamma rays do not penetrate the ground as far as radio waves. That's because radio is not photons. All right, we're almost done. We have, I think, 3 more slides after this. Photons and temperature is the ending of the discussion today. Photons are pieces of the wave functions. They're 2 dimensions out of 3. But how is the photon frequency related to s, the speed of the wave function? Now, temperature is about the velocity squared of electrons or ions. Photon emissions depend on the temperature of matter. But how is temperature changing? S. How does S get affected by temperature? These are questions for science to answer. And I'm going to answer it in about 3 seconds. All right, temperature units of measure. The temperature is a potential, T. And all potentials, like voltage, is velocity squared. Temperature equals meters squared per second squared for electrons and protons in a plasma. But that's contrasted with the speed of the wave function, s, which is meters per second, just inside one ion. And the equation there is talking about how Boltzmann's constant is really an area, because it's joules per degrees Kelvin, and joule is meters to the 4th power divided by second squared. Therefore, Boltzmann's constant is an area. Conclusion, part 1 out of 2. I tried variations of this theory, and future work is needed to resolve how the solar corona photons relate to S, the wave function velocity. But maybe the photon frequency uses this formula. F equals S times T divided by the circumference of the atom times degrees Kelvin. Now, if we set the speed of the wave function equal to the speed of light, and we set the temperature at 1.5 billion degrees, then the frequency of the photon emitted would be 2 times 10 to the 26 hertz. And as expected, gamma rays. This is a gamma ray frequency, and that would be emitted when the wave function equals the speed of light. And finally, in conclusion, we're almost done here. The photon's frequency can be as high. The photon's frequency can be a high frequency, even if the temperature is low, because there's two factors. For example, the corona of the sun might be only 6,000 degrees, while giving off X-rays and ultraviolet. So it appears to be much hotter. It appears to be 2 million degrees, but maybe it's only 6,000 like the rest of the sun. That's because S and T are two independent variables. S is the velocity of the wave function, and T, temperature, is the velocity squared of electrons and ions. Two very different things. S is a local velocity inside one ion's curved coordinate system, but T is the velocity squared relative to all exterior electrons and protons. So that completes the presentation for today. Thank you very much. I will now turn off the stream.